Hi, I'm Krey with Surface Water Solutions. I'm honored to be hosting today's Australian Water School webinar covering QGIS, or QGIS, however you like to pronounce it, for preparing and visualizing hydrological data. Now, today's webinar builds on our December 2019 QGIS webinar, where we covered some plugins that allowed you to do some things with hydrological applications. Have a look at that. Many of you joining us may have already seen that, but if you haven't, go to our website and you can have a look at that one as well. These webinars build toward some courses that are coming up. You may have seen those links as you were about to join. We'll be posting those links again in our recording and also at the end of the presentations today. Have a look at this map. Look at where everybody's from. 120 countries joining us, people from all around the world. Sorry for those who are in some nighttime time zones, but we try to accommodate the best we can. Now, the interest level in QGIS is growing all the time, and this, what we're covering today for hydrological applications, is just one thing you can do with it. Imagine the communities that are springing up around all sorts of other applications as well. So it's exciting. Thank you for everyone for joining us today. We look forward to the discussion with your expert speakers. Now, let me introduce to you Hans from Delft, Kurt from Bird's Eye View, and Saber from Locator Consulting. These are those who wrote the book. So if you want it straight from the source of those who are doing the coding and on the cutting edge of what's new and what's coming in QGIS, this is the dream team here. I'm going to start out by walking you through one quick exercise, a very basic thing before we get to the real experts, something to cover what we did last month on the Australian rainfall and runoff webinar that you can have a look at. Very basic task, which is getting the centroid of a catchment or a watershed. And I'll just show you a very quick tool on how to do that. Hans is then going to walk you through doing a catchment delineation. Kurt will then walk you through how to produce a map, a really nice looking map of your catchment or your watershed. And all along the way, Saber is going to be monitoring the question and answer line, the Q&A line, and we will then lead into a Q&A session at the end where you get to ask the questions. You can upvote them as you wish, and we'll address those questions in a live setting. Thanks for that. Now, having a look at the survey results, thank you for filling those out. I'm having a look here at how many people have been looking into QGIS and have experience with it versus some of the other software platforms. And with that, maybe I'll turn it over real quick to the others, to Hans and Kurt. Any comments on the survey results?
Well, hi, this is Kurt Menke in Albuquerque, New Mexico, and scrolling through the GIS software, QGIS is 74% of the users selected QGIS.
Yeah, that's great to see. And also, we have a lot of ArcGIS users here that can see the potential of QGIS in this webinar. So I think there's great potential for all of us to demonstrate what we can do with QGIS in the theme of water.
Thanks for your input. I'm going to share my screen real quick. Looking at Brisbane and zooming in on the Gold Creek catchment, which we've used in a few of our courses before. This is a catchment that is in Australia, and last month we had over 1,000 registrants tune in on how to delineate catchments through the Australian rainfall and runoff data hub. So if I take a catchment, last time when we covered this, and you can go back and look at this, if I take a catchment that I upload through a shapefile, it's easy enough to get the data for that. If you have that as a shapefile, you might have grabbed that through ArcHydro or some other method. If you are able to upload that shapefile, you'll get all your information. But what about the RFFE method, where you need the centroid? This is where a tool like QGIS can come in handy. That's going to show us exactly what we need to do to get that centroid. Now, keep in mind, a centroid is the point through which if you cut it out of cardboard, it would balance on that point. All lines cut through that point will have an equal area on one side or the other. So in QGIS, you've got some handy tools here that, again, this is free software. Grab your centroid. And if you grab the centroid, all you've got to do, or to get your centroid, is just run the script. So I've just run it there twice, so I've got two of them. It's the same point though. So see that point in the middle of the green? That is going to be your centroid point, the balancing point basically. And so that's something that can be then just exported back as a shapefile. You can put it in the Australian MGA GDA coordinate system and grab that file, which is now just a single point. With that, you could take that into Google Earth. You could grab the coordinates from there, or we could export the coordinates directly. So that's something that could then be uploaded into the RFFE program. And in our case here, we've got a lot of HEC-RAS interest from this group. This is a HEC-RAS screen, which Razmapper is a GIS interface. You can have a look here, and you can pull that same centroid point. There you see it right in the middle, that same centroid point of the catchment that we'll be delineating in the course that we'll be offering as a follow-up to this webinar. You could also then export it as a KML, pull it into Google Earth. You can see that little place mark there. That's the centroid of the catchment. With that then, let me just pull up the next one briefly to show what you could do if you needed to get the actual numbers zoomed way in. This is again back into QGIS. You could, instead of MGA GDA, because you're asked for lat long coordinates in this one, you could go in and change the coordinate system. Now, I realize we're flying through this stuff very quickly, but that's the beauty of having a recording of this. You can stop it, pause it, and try to follow along on your own. So essentially what we're doing then is we can go in and get the attributes, which do not automatically have the latitude and longitude on them. And we can then use those these buttons and very quickly write an expression. It's just the $sign is really all we need. For decimal degrees, you're not going to be able to use whole numbers. Got to use decimal degrees. And then on the output, if I'm spelling that correctly, latitude, if I just put in there, it's just a $sign and an X, that's going to return with only a precision of 3 in this case, which might not be enough for you, but that will return the latitude. If I wanted to go back in then and ask for the longitude with this one as well, I could get that spelled there correctly. If I do an asterisk and a $sign and a Y, that's going to give me my coordinate. But you see, that's just to 1 decimal place. That's not going to help you at all. You're going to need to take that to probably 6 decimal places on that one. And then that way you can take and copy and paste these numbers straight into your RFFE software. And that's going to give you all sorts of information about the design flood, the 100-year 1% flood, and things like that. So it's very easy to do these tools. These are the basics. I mean, you can find this stuff online for any of these tips that I'm showing you here. We don't want to talk about what's old in QGIS. We want to talk about what's new. We've had these guys on before showing us some excellent material. And Saber, Kurt, and Hans, we're excited to have you on board. We're going to turn it straight over to Hans.
Thanks, Krey. So I'm Hans van der Kwast. I work at IHE Delft Institute for Water Education, where I teach a lot in QGIS, but also in other open source GIS and data management stuff. So great to have you all on board here. And I'm going to guide you through this presentation about stream and catchment delineation in QGIS. You might have seen similar presentations before, but I took a slightly different angle. So in QGIS, you have the graphical modeler, and you can basically build the whole procedure in the graphical modeler. So I'm going to use this diagram as a outline of this presentation. So the whole workflow is here in different boxes. Basically, I took 2 models to do this because there was one part that I couldn't pass to the next model yet. Maybe in a future update of QGIS that's possible. So here in yellow, you see all the inputs. And then in the white boxes, you see the different process, and in green, the outputs that are generated. And I'm going to guide you through all these different steps. So for the DEM acquisition, that's the first part to get these DEM tiles. There are different options. You can download the tiles from free resources. Very common to use for the larger catchments is the Space Shuttle Radar Topography Mission, SRTM, and the data is available through the USGS website. And also very often the Aster Global DEM is used. You have to check for your study area which one is best to use. The accuracies are different, the way of acquisition is different. Space Shuttle Radar Topography Mission obviously uses radar and provides you an approximate 30-meter resolution DEM of most parts of the world. Aster has a bit of larger coverage, but the data comes from stereo photogrammetry. And there are also some other products like the JAXA Global ALOS 3D World product, also a great product. And new products are coming out all the time. So there's the NASA DEM that has a combination of different sources to get the best cover, but I don't think it's completely out yet. And you should always check if there's great local open data that you can use. So just some screenshots of these portals. So there's the ALOS website where you can look for the data from ALOS, also around 30 meter spatial resolution, a screenshot from the USGS portal, and you can also use the SRTM downloader in QGIS to download all the tiles from SRTM for the area that you have on your map canvas. So that's the first step, acquire your digital elevation model. Also, it's important to realize there that the highest resolution is not always the best to use. It depends a lot on your purpose, and for catchment delineation, especially for large catchments, it's about getting the water flow and the boundaries. So really working with centimeter DEM or less than 5 meters is not very useful, and introduce a lot of problems in terms of calculation times, but also in terms of variability of your accuracy. So the next step is to mosaic your DEM, because often you're not so lucky that your study area, your catchment that you want to delineate is centered in one tile of the DEM. So you have to use a tool to mosaic. You have basically two choices. You can use the merge tool from the raster menu in QGIS, or you can use the build virtual raster tool. And it's more efficient, common to use the build virtual raster tool, because you don't need exactly that data to be saved on your disk all the time. And what it does, it virtually builds a raster that you can use for further calculations. So you lose the tile boundaries and you can continue with that. Then the next step, so we are now here in the scheme, we did the mosaicing, is to reproject and clip the DEM. I've put them in different boxes because it depends a bit on the tools that you use. You can have tools that merge different processes and you have them separated out, but it's good for us to know why certain steps are happening. So let's first look at the projections. Normally data that you download are not in the projection that you want to use for your project. And global data sets are often in the geographic coordinate system, which means that the coordinates are in latitude, longitude with units in degrees. However, for DM analysis, it's very important that you reproject it to a coordinate reference system, which means it has units like meters. So why is that an issue? Well, let's look at this graph, and we see on the x-axis the distance, and on the z-axis the elevation. And when we do all kinds of calculations with the DEM, we need to use these x, y, and z units. And the computer is expecting that they are in the same units. So if that's not the case, you need to convert it. So if we want to calculate the slope, we do basically delta z over delta x, and we take the arctangent to get the slope. If the z is in meters and the x is in degrees, things go wrong. Now you might wonder what will happen if you do this on a map, because here we have a line, but in the map we have pixels with different elevation values. So what it basically does is it will use a moving window that goes over your raster, and it will look in the 8 surrounding cells in 8 different directions, and it will choose the steepest slope that it will assign to the center of the cell. So it's a focal operation that is used there. So it's always good to realize what a GIS is doing when you push the button for calculating the slope. So after reprojection, you need to clip the DEM. Subset is a technical term for making your raster smaller and fitting approximately your study area. There's a good reason for doing that. So remember that in this example, we had these 4 tiles. That's quite large to process I advise to have at least 16 gigabytes of RAM in your computer when you do these kind of analysis. But then still, if you have really large DEMs or very high resolutions, you will run into problems. It will give errors, or your computer gets stuck for a long time. So you need to clip it. And in courses, we normally provide you with a bounding box, which in reality you don't have. So I often get questions like, where's the bounding box? Where I can download the bounding box? Well, there's where you as a water professional need to use your expertise and look at the DEM and approximately with your knowledge guess where the boundaries are of your study area. So here in this example, we have the 4 tiles from around the Ruhr catchment, and I made it a bit smaller, highlighted it here, and that's what I clipped out. You should also be careful not to make it too small, because when you make it too small, then you will have in the end a catchment that has some square boundaries that don't look natural. So really do a good guess or do it in an iterative way to get the best result out of it. After that pre-processing of your DEM, there are a few more steps needed. There can be voids in your data. So we're now in this step. We have download DEM, mosaic the tiles, reprojected and clipped it using a bounding box based on expert knowledge in reality. And now we're going to look at this step, filling the voids. Basically, it's interpolating of no data. Especially in areas with much relief, there can be these no data patches in your DEM. And you need to remove them, otherwise, the water cannot flow through it. So you can interpolate them using a tool, fill no data. There are also more advanced ways of doing that, but that's the basic method to do it. And if you now look at the picture on the right, you can see that what happens is it will take the information from the surroundings and interpolate those voids. Of course, that doesn't generate the real data, so always be aware if you have big patches, you might want to combine different data sets to fill it instead of doing just an interpolation. But it's essential to do that if you have voids. There's a video on my YouTube channel where you can see the procedure. After interpolating the voids, we go to the next step, which is about filling the sinks. That is essential for hydrological analysis because there are depressions in the data. And they are an artifact based on the creation of the DEM. And they make that the water gets trapped into depressions. So these are not no data cells, but these are cells that are artificially lower. And we need to fill them up or cut through in the surroundings to make sure that all the water that falls in the area reaches the real outlets. If you have real depressions, you need to add them in later. So in the figure on the right, you can see what happens. So here we look at the side of a DEM and we have the flow direction of the water. And there the water can get stuck in this hole. And what the software can do is either fill it up or it can cut through so the water still reaches the outlet. Now that's manipulation of the data to make it hydrologically correct, which is already making the model that we're going to use. So it's not necessarily closer to reality. It's closer to hydrological reality where all the water can flow to the outlet. So keep that in mind. And you can, with QGIS, do the filling sinks procedure with different tools that are available from the toolbox. Most commonly, we use the fill sinks algorithm from Wang and Liu. And if you have a very large or high resolution data set, you can use the XXL version. It's a robust method which keeps the downward slope and should work under most conditions well, but you could also try the other algorithms. Once you've done the filling sinks, you can compare with the profile tool what happened. And here we have this big lignite mine in Germany. And it clearly shows us what happens if we use the fill sinks algorithm. It will remove the pit. So on the red line here, we see this cross-section for the DEM that was not filled from SRTM. And then after filling, the green line shows that the whole pit has been filled up and the water can flow through it to the outlet. which is not realistic from a point of view of creating a realistic DEM, but essential to create a hydrologically correct DEM. And the next step is that we need to derive the streams. So once we have a hydrologically correct DEM, we need to do a step that is different in different procedures. So we could look at flow accumulation over the DEM and then decide a threshold for which we call it a river. Here I choose to explain another method which uses the Strahler orders, which is a bit more intuitive. So let's have a look. Basically, the flow accumulation and the Strahler order method uses the flow direction. And the flow direction uses a similar algorithm as the slope. It looks, when we use the D8 algorithm, in 8 different directions and chooses the steepest slope downward. Therefore, it's called the D8 algorithm. That's a very robust method, but for flatter areas or with a lot of diverting slopes, you might want to choose for the D-infinite algorithm, which uses continuous directions. You can calculate these through the Saga tools in the processing toolbox. This tool, Channel Network and Drainage Basin, is basically a collection of different scripts that calculate different outputs that you might need in your hydrological analysis. You can visualize the flow direction using a directional ramp. And Kurt explained very well in the book and in our QGIS Hydro webinar how to make that. Because directional data, we cannot really apply a linear color ramp to it, because then, for example, northeast and northwest will be furthest from each other and north and south will be closer, which is not really giving a nice impression. Still, it's very hard to interpret these flow direction maps. So a better way of representing it is using arrows. And it's a great tool that I developed together with Lutra Consulting, with Saber's team, where we can convert the Saga output from the flow direction to a mesh format, to a grep file, and then use the very nice new tools in QGIS to deal with mesh data, and to use the mesh visualization to get these arrows on the map. And you can even view it in the 3D view like this and get a good interpretation of water flow in your study area. So definitely you should have a look at that way of visualizing your flow directions. So in this case, I don't use the flow accumulation, but I use the Strahler ordering mechanism. And this method basically starts with labeling all your pixels with Strahler order 1. And when, according to the flow direction, 2 of the same order join, we increase the order number. So 2 of 1 join, we get order 2, and 2 of 2 join, we get order 3, etc. When a lower order joins a higher order, we don't change that higher order. So it really needs to be of the same order. As you see here, 2 times 3 becomes 4. So that's a step we do. And then we need to choose a threshold to choose which Strahler orders we consider as the rivers. So if I visualize all the Strahler orders with a blue ramp, we can see the flow patterns already. But now the trick is to determine which value you use as a threshold, larger or equal to a certain threshold, to be considered as a stream. And you do that in the raster calculator. This is a calibration method where, again, you need to compare the result with rivers that you can see on a map or a satellite image that you can use as a backdrop. And then the result will be this, rivers with different Strahler orders. The next step is to define your outlet. And since we have been making a model, the outlet is not exactly at the place where you see it on the map. So in this case, the outlet of the Ruhr River in the Meuse, where it gets into the Meuse, is approximately here. But the delineated stream is over here. This difference is caused by our model. And because of a lot of urbanization happening here and manipulation of the water flows, which we are quite good at in the Netherlands, to manipulate the water flows. But you should realize that you work with a model. So you need to snap this point to the line. Either you move it manually to the to the line that we delineated, or you use the snap geometries to layer tool, which with a certain tolerance can snap the point to your delineated stream. An outlet can be any point in the river, maybe where you have your discharge measurements or your other measurements that you need, or it can be an outlet of a tributary, like in this case, or where it gets into the estuary or ocean or a lake or a wetland. But in all cases, you need to move it to the delineated stream. And then we add the X and Y fields to the layer in a similar way that Krey showed before. But here there's a tool that does it automatically for you. You can find it in the toolbox. And that gives us then the snapped outlet in this whole set of tools in this model, which, by the way, you can download from my GitHub repository. After doing that, I move to the second model, which is a bit shorter. That's to delineate the catchment. It uses the filled DEM and the X and Y coordinates from the snapped outlet that was created in the previous graphical model. Then it uses the tool to delineate the catchment, but that's still raster. And what we want is a nice boundary in vector format. So I need to polygonize and save only the catchment out of it. And then the end result is the catchment boundary. So we use the snapped outlet from the previous step. And then we use this upslope tool from the processing toolbox to create the catchment boundary. That's in the raster format, so you get something like this. That's this layer, the catchment. It has 0 and 100 as values, where 100 obviously is your catchment. And then we will use the polygonize tool from the menu to turn the raster into a polygon vector. And then you get something like this. And you need to then remove the outside area, and you can do that by checking which value, it's 100 normally, is the catchment, but you see that there are two values of 100 here. It has to do with the fact that if you polygonize a raster, you might get little loops and geometrical errors around the side. So you can just find the largest catchment polygon and then invert the selection and remove the other parts, so you remain with the catchment boundary. And then you can still later get geometry errors, which you can fix by using fixed geometries from the processing toolbox. Then the last step, which I'm not going to pay a lot of attention to, is styling the results. You can have a lot of fun with styling. So you see here some different results for the Ruhr catchment. And I'm sure that Kurt's going to tell you after this presentation quite a lot about all the new tips and tricks in QGIS for making your maps. You can see a whole chapter dedicated in our book, QGIS for hydrological applications, on the styling, if you want to do it step by step. And yeah, how can I learn more? Well, first of all, join the session organized by the Australian Water School on the 20th of August. So there are two sessions, and one session is about this whole procedure of delineating the catchment. And we're going to delineate the Gold Creek in Australia. There you'll see more in Kurt's presentation. You could also join our online course, QGIS for Hydrological Applications, organized between 14 and 18 September by IHE Delft. And Kurt and I will be giving there also live assistance. As mentioned, you can also get the book and follow the steps there. And if you want to look for free materials, go to gisopencourseware.org. And if you want to be in touch with me, follow me on social media and follow hashtag QGISHydro to see what's coming up. So I'm going to hand over to Kurt to see if there are some questions coming in. Stop sharing this screen. Hi, Kurt.
Hi, Hans. So while I'm getting set up here, Saber, did you see any questions that came up on the session that look interesting to answer while I'm getting set up?
But a question was, can you calculate, that's probably for Hans, can you calculate Muskingum X and K parameters in any of open source GIS you're aware of?
I'm not aware of those variables. Maybe it's more from hydraulics. I don't know if Krey knows those, but if I get the equations, I can probably implement them. You could also try yourself. I did a few of these equations that are quite common in hydraulics. There are some new videos on that, but not particularly these ones.
Yeah, that one will be more of a HMS if you're into the Army Corps software. There's other software that'll do it as well. But yeah, if we, this is open source stuff. If you have something that ought to be built in and would be convenient and handy to have, that's the beauty of this. It can get built in.
And there are lots of questions about sampling. How would you fill in null areas? What methodology do you use usually for topography?
Well, yeah. So if you need to acquire data and you have holes in your DEM and the filling, the interpolation of those voids doesn't work, then you probably need to acquire data or digitize contour lines from existing maps. Yeah, there are few more manual solutions to do that.
All right, so I'm going to move into my presentation, and we can hopefully get some of those other questions answered in the chat as we move along. I'm going to be talking about visualizing hydrological data in QGIS. I'm Kurt Menke. I'm with Bird's Eye View and the Q Cooperative. I'm a consultant, so I wear a lot of hats. I do some spatial analysis, some cartography, and some teaching. I'm a QGIS certified instructor, meaning I can give out official QGIS certificates to attendees of my courses, and I'm an OSGeo charter member. I'm also a QGIS author. I'm a co-author on QGIS for hydrological applications with Hans van der Kwast here. And last year I also published Discover QGIS 3X, which is a large, complete, thorough treatment of QGIS. So those are both available through Locate Press. And so I'm going to talk about styling in this presentation. And when we do a hydrological analysis, we always start with a DEM. And when you first add an elevation data set to a GIS like QGIS, it comes in stretched from black to white. So here we have the DEM that we'll use for the Gold Creek catchment analysis brought in. And so what we can do is color that and then generate a color hillshade. So I'm going to walk through some of the steps to see how we would create that. And one of the nice things with QGIS is that obviously we can go into the properties of a layer, and you'll find a Symbology tab there, and you can work with that, the styles that way and labels. But every time you make a change, you have to click apply. So instead of that, we have a much nicer tool. Like clicking F7, we can open up the layer styling panel, and this gives you complete access to all the styling options, but you get immediate feedback on what you're doing. So when you choose a color or classify a layer, in this case, you will see the result immediately on the screen. So it's a really nice intuitive way for you to start styling your analysis results when you're done. So let's look at how we might set up a color hillshade effect. So here we have the Gold Creek DEM, the filled one from the analysis. And we can see in the layers panel that we have the elevation range, and it's again stretched across this black to white color ramp. So first what we're going to do is change it from this default single band gray renderer using the styling panel. And I'm going to instead use the single band pseudo color. And that allows me to choose a color ramp. And there's a whole set of color ramps that QGIS comes with. And I can click classify, and I have now a nice terrain set of colors for my DEM. And now I'm duplicating this DEM. I'm going to bring the duplicated copy of this to the top. And QGIS also has other renderers for DEM. So I can now change for this copy of the DEM to a hillshade renderer. And voila, my DEM is now styled as a hillshade. QGIS also comes with these things called blending modes that you'll find in lots of other graphics programs. So I'm going to choose a blending mode of multiply. And in just a few seconds, I have a beautiful color hillshade of the Gold Creek area. Another new tool that just came out in QGIS 3.14 is a hillshade renderer. So now if I make another copy of this DEM layer, and again go to the layers panel, I'm going to choose a contour renderer for this DEM. So now my DEM is going to be styled as contours. I can set the interval. I can even set the interval for an index contour and set the special line thickness for those index contours. And then all my other styling options are available too. So I can change set a blending mode, for example, for these contours to create a nice effect. So here we have a DEM styled in three ways: as a color DEM, as a hillshade, and as contours to make a beautiful effect, and you can do it quite quickly. So once we've done that and we run through our analysis, whenever you produce a layer in QGIS, it's going to come in with random symbology. So here we have the Gold Creek catchment that will be covered in the course in August 20 and 27th. And the catchment is this kind of hideous pink color by default. That's just what QGIS chose. And the streams are actually blue, but we can improve this. So Hans talked about the Strahler order. And what I can do to make this a more intuitive analysis result is use a graduated renderer for those streams. And one of the attributes that was produced when the channels were generated was an order attribute column, which contains the Strahler order. So I can classify this based on the Strahler order using the size method so that I end up with thinner lines for the Strahler order 1 streams and thicker lines for the Strahler order 4 streams. Now, if we want to style the catchment, we have some really nice options here. So in QGIS, we have an inverted polygon renderer. So I'm going to style here the catchment boundary with an inverted renderer, which makes it equal the opposite of the catchment, everything beyond the boundaries of the catchment. I'm going to combine that with a shape burst fill and give it a little bit of transparency. And when I turn this on, it just kind of provides visual focus to the catchment. You can still see the terrain around it, but it's a really nice effect for focusing your map reader's attention on the result of your analysis. So now I'm going to walk through how to make a map and show the results of our analysis. So in QGIS, you use the print composer, which opens up in its own window. And along the left-hand side, we have all these buttons for adding different map elements. And right now I'm adding the actual map to the map canvas. I can change the scale, and I can use some tools to slide the map around and center it so that my catchment fills up the center of the map. And as we go through this, we want to add all the other map elements. So it's always important to have a nice, clear, concise title so that the map reader knows what they're looking at. So here we're looking at the Gold Creek catchment. And along the left-hand side, you'll have these different buttons for adding things. So I use the text tool to add the title. And next, I added a map legend. This is the map legend tool. And so I just added the Gold Creek catchment and the channels here. So another nice advantage of using 3.1.4, the latest version of QGIS, if I open up the style manager here, this is something that QGIS comes with and has had for a while that allows you to organize your styles for markers and lines and fills, color ramps, all sorts of things. And you can tag symbols. So if I choose the color ramp tab here, I can choose terrain and see which color ramps I've tagged as terrain color ramps. We also now have a tab for text format so that you can store titles. There's one for label settings. The one we're going to focus on here is legend patch shapes. So I can make custom legend patch shapes. For example, here I've created a legend patch shape that is the Gold Creek catchment. Under hydrology, I have a bunch of stream symbols as well. And you can create these. So in QGIS, you can go and create using an expression using different geometries, a legend patch. So here what I've done is to our map is updated the legend. So it's now using the legend patch shape of the actual catchment in the legend for the Gold Creek catchment. And it's using these nice little river symbols for the Strahler order streams. Anything you can do to make everything more intuitive to the map reader is a win. So here we're going to talk about the scale bar and the north arrow. So here a scale bar has been added, and QGIS comes with a whole suite of different scale bar options. And this just allows the map reader to judge distances and scale on the map. So it's an important map element. And here's the north arrow. Especially it's possible to rotate maps. So if a map's been rotated, a north arrow should always be there so people know which way north is. Helps them orient. And in QGIS, there isn't a quick, easy way to add a gradient legend for our elevation here, but we do have a workaround we can use. Here I've added a rectangle to the map, and just filled it with the same color ramp that I'm using for my DEM and put little labels on there so that I have the representation of the elevation on the map for the map reader. And lastly, we want to add a locator map. People may not know where the Gold Creek catchment is in Australia. So here in the main QGIS window, there's this little eye symbol, and this is for setting up map themes. So here I've turned on a map theme for the locator map, and I have my bookmarks panel down here so I can zoom to the Gold Creek catchment or all of Australia. And so I basically have two different maps saved, one which is the locator map and one which is the main map. And the locator map is just going to be the states of Australia, very simple, labeled. Everything else will be the main map, our catchment. So when we get to our map layout, we can basically tell QGIS that this main map is going to be using the main map theme. We could add a second map and tell QGIS this is going to use the locator map theme. And we can then add an overview to this so that people know where in Australia this Gold Creek catchment lies. It gives them a little more context. And finally, there's a lot of nice options we have. And since we're working with elevation data, QGIS comes with a 3D environment. You can go to the view menu and you can open up a 3D view panel and extrude the, basically tell QGIS that the terrain surface is our DEM here, and here I've extruded it a little bit to exaggerate the relief. And you can here navigate in 3D. You can set keyframes, and you can actually create fly-through videos using this environment. So there's a lot we can do with this as well, and we'll cover this on the course on the 27th. So thanks, this is my contact information, and I think now we can open things up for questions. So
yeah, definitely. Hans, if you want to start your video again too. Saber, if you want to unmute and come online. Frantically answering questions there. There's been over 50 questions so far. I don't want to pick which ones we ought to, we'll give the audience the best bang for the buck. Let's let maybe Saber have the first stab at the ones that he's been answering that you think are worth covering, and then we'll just kind of banter back and forth with the questions that have come in. Keep them coming. We won't get to all of them, but upvote the ones you want to see the answers to. We'll at least hit the ones that get the most upvotes.
Sure. A question for Kurt, probably. Can you edit the legend items in QGIS?
Oh, absolutely. Yes. You can add and remove layers from the legend. You can edit the text, and obviously you can change the legend patch shapes now as well.
Brilliant. And a question for Hans. What's the difference between filling void and filling sink?
Yeah, I should be clear on my terminology. So you fill sinks and you interpolate voids. So in my future presentation, I will separate them more. So voids are no data values in your DEM, and sinks are depressions that you don't want in your DEM if the water needs to flow out. So they're completely different things, but both need to be removed.
Question for Kurt. Can you save the template for printing and reuse it for future?
Yes, you can save a template for your print composition and just have a collection of those, and you can load those every time to import logos and titles and things like that you're going to use on a regular basis.
Let me interject with one quick comment, just more of a logistical item for everybody, and then we'll get back into the technical bits. We have had quite a few comments coming in saying, wait, I wanted to join this and see exactly how to do it myself on the QGIS window. So you wanted to have that open and follow along on the steps. Now, there are some videos that will walk you through that. There are available, for free online. We recognize full well that in this forum where Hans and Kurt each have 15 to 20 minutes to show you something, all we can really do is demo some really cool things that QGIS was able to do. We recognize that constraint, and that's why we've set up a 2-hour session for both of the things that we've just covered. Hans will walk you through everybody who wants to join in on that. The places are limited, so we don't want to overwhelm them. But for 2 hours, you'll get to sit with him in a live interactive session and delineate a watershed yourself, or a catchment yourself, with the example files that we've just shown you. Likewise for Kurt, we're going to do the same thing. So in a couple of weeks, we will show you those links. That'll come up at the end of the presentation. Feel free to sign up for those. Yes, we feel your pain. We wish we could be here with you all day long, but there are plenty of resources available online. Kurt and Hans and Saber, if you want to paste any links in for things that you think would be valuable for those who aren't able to attend the course, but we encourage you to come on board and do this with us, together with us, so that we can all get make a whole lot more experts in QGIS. With that, back to the technical questions then.
Question for Hans. Is there a raster calculator algorithm for density?
Well, it depends. Well, you can calculate the equations, so it depends which density. It's just something divided by area.
Okay. And one question for Kurt. If we change the settings in QGIS for visualization, is there some way to save that so that we don't need to start from scratch next time when we load our data?
Well, yes, you can save symbols, for example. So I could, if that inverted polygon shape burst fill for the catchment, I could save as a symbol, and I can tag that under hydrology so that I can find it again easily. So yeah, you can save symbols for points, lines, polygons, text, legend patches, labels, all of that in QGIS.
I see a question here that is upvoted quite a bit about the SESCN method. I guess that's curved number. Krey, help me if I'm wrong there. But the curved number method is basically lookup table stuff where you use different properties of the landscape. So I don't see a problem why you can't do that in QGIS. As long as you have the tables, we can configure that and calculate the curved number method.
Yes, I didn't think we'd get quite that much interest in HMS given the odd hour of the night for our American viewers. But I see that was the most upvoted question, was about HMS. So come on board. HMS has got a new version out. Have a look at our previous webinar where we walk you through how to delineate catchments and build a basin model in that one. And then come along to our course where we'll cover that in, again, another 2-hour session on using those new GIS tools, and then another follow-up session on just building a basin model in HMS. So that's something that is certainly coming up, and I've just hit answer on that question. So now our next most upvoted one deals with groundwater. I'm not a groundwater guy, so I can't tell you. ModFlow. Any of you guys, Kurt, Hans, Saber, have seen groundwater tools built into QGIS like ModFlow?
Yeah, FreeWatt is already mentioned there. I think that's an interesting one to look at. It's a nice plugin, came from a European project, if I'm right, and some colleagues from IGRAC have been working on that. But there, yeah, definitely tools coming in for that all the time. By the way, we are giving a free ModFlow course at this moment in the open courseware of IHE Delft. We had our first session on Monday. The next one will be on Friday. So check the IHE open courseware page and look for the ModFlow course and join for free.
Thanks. And this will be just a kind of a free-for-all among all the presenters here. Have a look at the answered questions. We're up to 70-something questions now. Some of them have been answered without the chance for people to upvote them, really. So if you see any in there, you might want to scroll through those as well and see if there's any that ought to be covered live. So I'll just leave it to everybody to chime in as you see fit.
I have another couple follow-up thoughts on styles. So there's been a couple more advances in managing styles in QGIS. So first off, what I was talking about before is all in that style manager, that one slide that I showed. But you can also now, in the browser panel in QGIS, right-click on a QGIS project file and export all the symbology and the layers contained in that project file into a style database. And there are now also several processing algorithms in the toolbox that you can use to manage styles in that way and style databases. So I encourage everyone to dig around in there. There's a lot in QGIS now related to styles in recent releases.
Okay. Saber, I see you've answered a few that you might want to bring up.
Yeah, there is a question. Can you create several maps if you have a large catchment to use the same kind of composition? I can answer that. Yes, there is a function in QGIS, atlas printing. You set up the print template or the print frame, and then it can go through different grids or polygon extent and create similar maps for that. And there is another question, can you display contour, hillshade, and the color ramp of a raster all in one map? I can ask Hans to answer that.
Yes, you can. I think Kurt showed already some examples of that. So great thing is using blending modes, and vectors can just be plotted on top of that. And in the newer versions, you can have the on-the-fly rendering of the contour line. So basically, you can combine all the data as long as you use the blending for rasters. Transparency makes it a bit hazy, so that's not the best way.
And the question for Kurt, how did you create the horizontal legend for raster, for the elevation raster?
So in the print composer, I simply added a rectangle. There's a rectangle tool. And I then filled that with the same gradient, using the same, with a gradient fill, using the same color ramp that I had used for the DEM. And so in there, you can orient that gradient fill so that it's, you know, in that case, going left or right across that rectangle. And then I simply added text for the elevation max and min.
A question about how did you create both the geometry, the custom geometries?
Yeah, for the legend patches. So you can basically put a feature such as the Gold Creek catchment into edit mode and hit Control-C on your keyboard to copy that geometry onto your clipboard. You can then open up the style manager and go to that legend patch tab, and you can open that dialog for creating a new polygon legend patch and paste that feature, which is represented as JSON at that point, into that little box, and create your custom legend patch from a feature that way.
And the question for Hans, how would you do the subcatchment delineation?
Yeah, that came up quite a bit. Well, basically, if you can do it for a catchment, you can also do it manually for a subcatchment, and you can automate that for different points if you know the outlets using the graphical modeler. But together with colleagues again from Lutra Consulting from Saber, we made a little tool which is on my GitHub, where you can load a point layer and it will delineate all the subcatchments based on that layer. If you want all the subcatchments, then you can also export the junctions from the channels tool. Then you have all the points that are on the junctions of the tributaries, and then use that as an input to the delineation tool that's on my GitHub.
It's about accuracy of DTM and how do you define the accuracy, but
I think that's a good, yeah, that's something good. I can say a few words about that. So yeah, generally accuracy depends on your purpose. That's the starting point. So why do you need a certain accuracy? So if you want to delineate the whole Amazon River, then probably you don't need a very detailed DM, and you should also not confuse accuracy with resolution. Resolution is more about precision. So first look at your purpose. And then people ask, yeah, how do I know how accurate the watershed or catchment is that I delineated? Again, that depends on your purpose, and you make a model. So the GIS tools provide a model to delineate it, and different tools give slightly different results. But in the field, you can only see what you can see. So that's another, and that's also interpretation. So basically you're a modeler. So you need to take a decision there on what's the accuracy that you need.
Yeah, and I see that question within some of those questions that actually got the most upvotes. It relates it to dam break studies and other hydraulic functions. Now, keep in mind what we're doing today is hydrology. This is delineating catchments and the paths that water is going to take. from a satellite-based terrain surface, you can generally do okay for large catchments, maybe not for the small watersheds or sub-watersheds, but you can do okay. For hydraulics, like when you're talking dam break studies and things like that, we need to distinguish between the two. You cannot use this 30-meter DEM set for the shot from space to do any sort of channel definition whatsoever, unless you're working in a channel that's, you know, kilometers wide and has bathymetry burned into it. So that kind of accuracy, when we're talking about, you know, not just precision, but also the accuracy of the information, is not sufficient for hydraulic studies. You're going to need to get something more efficient. Most countries have their own repositories of better than 30-meter SRTM data. Some countries do not, and those questions have come up a few times here. How do I get it for my own country? And everybody's got their unique databases. And just keep in mind, satellite-based data is not going to work for getting velocities and river depths and the kinds of hydraulic parameters you want to extract from a hydraulic model. This is hydrology that we're dealing with here, catchment and drainage patterns. Anybody else want to chime in on others?
I have one last question. I can quickly answer that. It's upvoted as well. What do you mean by hydrologically correct DEM? Like, for instance, huge pit from a mine. I think the idea behind it that every drop of water eventually ends up in the sea. So all those sinks and lake areas, when you do hydrological assessment, you need to give a gentle slope to push water out. So we apply unlimited volume of water on top of DTM to create that gradient to gently push water from rain all the way to the sea. Obviously, as there are lots of assumptions, and it's just to create the streamlines from the terrain.
Yes.
Hans, feel
Yeah,
free.
correct. Yeah.
Good. Well, I think we're just about out of time here. So on the hour, let's, this one of the most upvoted questions was, is the recording available? Yes. Go to the Australian Water School's homepage or YouTube page, and you'll be able to access all of our previous recordings that we've referenced today, including this one. Do take this survey and do sign up for these courses. Again, we recognize that this is just a brief overview. We've thrown a lot of information at you, shown you some cool stuff that it can do, but we recognize that it's not something you're going to be able to do interactively and live on the fly while we're walking you through it, unless we have more time. So come join us for our 2-hour courses that are coming up. We have other on-demand courses for 1D and 2D modeling, 2Flow and HEC-RAS coming up, Python scripting, what's coming up in live training, and live training is live face-to-face through Zoom these days. Someday we'll get back to what we like to do, which is come out and visit you directly. These days, again, it's awesome to see this many people come on board. I'm going to turn it over to the others for some closing remarks, but just for myself, seeing everybody in this, in this together and trying to do some good with what you're doing out there in the divisive world. It's just, heartening to see rather than in contrast to some of the disheartening news we sometimes see. We can't get together in a stadium, but looking at these numbers, you guys would all fill a stadium. So I'm talking to this webcam. It freaks me out to think that there's a whole stadium of people watching this, but there is, and we're not able to be, arm in arm together, sitting next to each other, shaking hands. But virtually, we're all in this together. Let's do some good with this. So I do look forward to seeing you all online. Kurt, Hans, Saber, thanks for coming on board. Any closing comments from you?
Yeah, and we covered 2 hours of material in 15 minutes each. So if you're really excited about this, think about signing up for one of the courses.
Sure.
Excellent. All right, Hans, anything to add?
No, I think that's the best thing to do. If you want to know more, go to sign up for our courses and check us on social media. You'll find a lot of resources.
Great. Saber, final closing remarks.
Thank you very much to everyone for the great questions. It was a pleasure answering or participating in this meeting, and looking forward to seeing you all in the future events.
Sounds good. It's an honor for these to me to be in the company of these experts. These are some of the best people in the world, not just in what they do, but just in who they are. I've watched some of their webinars. I've interacted. We've had geo beers after some of the presentations they've done. This is how we interact these days in the meantime until we can do it face to face. And these guys are really making a great go of it. So thanks so much, everybody, for coming on board. With that, we'll sign off.